All right, so we're going to cover everything that is tested on the periodic table trends quiz. So we need to cover a couple of different periodic table trends, as well as some other information that is presented in the organization of the periodic table. So let's start with the basic way that the table is organized. The table is separated out into rows and columns, and we actually have special names for those rows and columns. Everything in a column, everything in a column, so one of these up and down columns, is said to be in the same group. So when you see the word group, you need to think column. Those are the up and down pieces on the periodic table. Everything in the same group has the same number of valence electrons. The same number of valence electrons. That means that everything in that group has the same number of electrons in its highest energy level. So if this is the nucleus of my atom and it's got some protons and some neutrons in it, I'm not going to spend too much time drawing protons and neutrons, right? I can represent energy levels with these ring shapes on a Bohr model. So whatever the highest or furthest out energy level exists, the valence electrons are the electrons that are in this outer energy level. So like this, this right here would be a valence electron. Anything below that is inner electrons. Valence electrons are special because since they're on the outside, they're going to be doing most of the interacting with the rest of the world with other atoms. So when it comes to how atoms react with one another, what sorts of things will form new compounds or won't, that has everything to do with these valence electrons. So because of that, things that have the same group or the same column and have the same number of valence electrons have very similar properties, both physical properties and chemical properties. So, same valence electrons means same properties, or at least very similar properties. And I'll move this note down here so we don't forget. This especially goes for chemical properties like reactivity. Things in the same column tend to react with the same sorts of atoms, chemicals, materials, all that good stuff. Whoops. It didn't save my writing. That's sad. Let me write it out one more time down here. Same valence electrons means same properties. So if you were asked to pick something, pick an element that is very similar or has very similar properties to some specific element on the table. For example, let's say that I wanted to pick an element that was very similar to sodium. Any other element in this column would be a pretty good choice to be similar to sodium because it has the same number of valence electrons. So when you go to justify that, you want to back up your answer by talking about the number of valence electrons. So that's about groups on the periodic table. What about rows on the periodic table? What about these? I keep having my eraser on when I don't mean to. What about these rows on the periodic table? Things in the same row, also called a period. That's where we get the period in periodic table. Things in the same row have the same same number of energy levels. So again, that means that they have the same number of energy levels, same number of levels where we can keep electrons. Each energy level is further and further out from the nucleus of that atom. So everything in the same row has the same number of energy levels. They do not have the same number of valence electrons. The valence electrons will change as we go across the rows. So things in the same row can still be quite different. The properties of cesium, for example, which is right over here on this corner, are very different from the properties of, say, polonium over here on the right side. They might be in the same row, but they are pretty different in their chemical and physical properties. So we need to know how many valence electrons we have for certain elements. So I'm going to go ahead and just block out this middle section. We're really not going to worry about anything in this middle area. These are all called transition metals. They can be kind of funky when it comes to valence electrons and stuff like that. So we're just not going to worry about them right now, and we're only going to focus on the parts of the table that I am going to highlight right now or box in green. So for the purposes of our discussion right now, the periodic table is just these things in green. The rest of it we can worry about some other day. So let's go ahead and make a note of how many valence electrons things are going to have. Again, everything in the same group, the same column, has the same number of valence electrons. Everything in group 1 has 1 valence electron. Everything in group 2 has 2 valence electrons. Everything in group 13 has 3 valence electrons. You can probably see a pattern. 14 has 4, 15 has 5, 16 has 6, I'm running out of room here, 17 has 7, and 18 are noble gases. All of them have 8, except for helium. Helium has 2. The reason helium is an exception is it only has 1 energy level, and that first energy level on helium, just going to draw 1 dot for our nucleus, our first energy level on helium can only hold a maximum of 2 electrons. So since it only has that 1 first small energy level, it can only hold 2 valence electrons, not the usual 8. So it is the only one of those noble gases that only has 2. All right, so we've talked about the way the periodic table is organized, how there's different numbers of valence electrons for everything in the same column or group. And we talked about how there are rows or periods with the same number of energy levels, right? With each of these rings on our drawing representing an energy level. So 1, 2 energy levels in this little drawing over here. There's one more thing related to groups and periods that I wanted to touch on, and that's that we also have some specific families that we can talk about with this periodic table. So I'm actually going to open up a brand new canvas here because this can quickly get kind of crowded. So let's open up a new periodic table. Okay. So we have some specific families on the periodic table. Everything in the first column is in a family oops, almost everything in the first column, is in a family, I keep having my eraser on, is in a family called the alkali metals. Hydrogen is not, because it's not a metal, but all of these in group 1, except for hydrogen, are alkali metals. And I learned my lesson on that. Let's just go ahead and write that with the pen, or sorry, with the text box tool. Okay. Alkali metals, and I'm going to color code these light blue. All right, right next to them, we have a very similar named family called the alkali earth metals. So everything in group 2 is an alkali earth metal. They're both pretty similar. Alkali metals are more reactive with certain things like water and oxygen than alkali earth metals are. But both are groups of metals. They're soft and shiny and tend to react fairly easily with various chemicals. So let me box that one in a darker blue color. We got alkali metals and alkali earth metals. We have some families for 13, 14, and 15 and 16, but honestly, we're not going to worry about them as much. We don't talk about them quite as much as some of these other ones. Right here, 17, this one is special. These are the halogens. The halogens. And halogens are often gases at room temperature, and they tend to be very reactive. So those are our halogens. And then finally, our last family that we will worry about knowing about is the noble gases. So the noble gases right here are in this last column. They include helium, even though it only has 2 valence electrons, because helium has a full energy level. So it behaves similarly to the noble gases. What's special about noble gases is they really don't react or form ions. They're very stable. So sometimes we say that the noble gases are noble because they're like royal people or nobles, and that they're like snooty and don't want to interact with the other common elements. They think they're special. Really, it's just because they're very stable and don't tend to react. So those are 4 families that we need to make sure that we know. The other big group being these transition metals, which we just know that they're called the transition metals. We're not really going to worry about anything else specific to them right now. Just know that they exist, and we call them transition metals. I'll label those real quick. All right, with the knowledge you have so far, you have the ability to navigate the periodic table. So for example, if I asked you to find a halogen in the 3rd period, I would know, or you would know at this point, to go look at the halogens, column 17, and the 3rd period, here's 3, periods are rows, so the halogen in the 3rd period would be chlorine. If I asked you to find an alkali earth metal in the 5th period, we would go look at the alkali earth metals, and the 5th period is right here, 5, so that would be strontium. So now you have the ability to find just about anything you could want on the periodic table. Let's talk about some trends or patterns that happen with atomic structure and some properties of elements on this periodic table. So again, I'm going to open up a fresh one here. Okay, Here's our fresh, clean periodic table. We're going to start with an easy pattern or trend called atomic radius. Atomic radius. The atomic radius of an atom basically just means its size. How big is it? You might remember from math class, especially if you're taking geometry right now, that the radius of a circle is just the distance from the center of that circle to the edge. So if you have a bigger radius, you wind up with a bigger circle. You have a smaller radius, you have a smaller circle. I'll draw a smaller circle within our bigger circle. Maybe. I'll just draw this one here. So as you can see, the radius on this one here is much smaller than our red circle. Okay, so the radius for an atom is, again, the distance from the nucleus, the center of that atom, to the highest energy level. Atomic radius increases as we go down the periodic table. We also say BAB, or bigger atoms, at the bottom to help us remember that. And it also increases from left to right. We can also say LAL, larger atoms to the left. The reason these trends exist has to do with two things. One, the number of energy levels, and two, the number of protons in the nucleus. So, when it comes to energy levels, like we said earlier, increase as you go down the periods on the periodic table. So hydrogen only has one energy level, while francium down here, covered up by my arrow, has 7. That's a really big difference. One energy level, which I'm trying to draw here, versus 1, 2, 3, 4, 5, 6, and you can see I probably can't even fit this on here, 7. So that is a huge difference in size. If you increase the energy levels, you increase the radius. That means if you're comparing two things in the same group or column, for example, let's say we were looking at nitrogen versus arsenic, the one further down would have the larger atomic radius. So arsenic would be bigger than nitrogen. But what about across, right? We go bigger from left to right. That's because things on the left end of the periodic table have more protons in the nucleus than things on the right. For example, fluorine. Fluorine is an atom that has 9 protons in the nucleus. And only 2 energy levels. So we have a nucleus with 9 protons, and we have just 1, 2 energy levels that are holding our electrons. Ooh, it's a very large electron. All right, 1, 2. For fluorine, it also has 1, 2, 3, 4, 5, 6, 7 valence electrons. Compare this to something in the same row or period, lithium. Lithium only has 3 protons in the nucleus. And it still has just 2 energy levels. Excuse my bad doodles here. And it just has 1 valence electron. So the thing about the protons in the nucleus, right, is that each proton has a positive 1 charge. So that means that a lithium atom has a +3 charge, while a fluorine atom has a +9 charge. So that's 3 times more charge in the nucleus on fluorine than on lithium. That means every single one of these electrons is being held 3 times more strongly by the nucleus of a fluorine atom compared to a lithium atom. If the attraction between those negative electrons and positive protons is strong, that means that the fluorine atom is actually going to hold those electrons a little closer to the center of the atom, compared to lithium, which has, all things considered, pretty weak attraction between the nucleus and the electrons. So I'll just draw kind of a shrimpy, weak arrow going in versus these really big arrows representing the pull from the nucleus to the electrons. So, things over here on this end of the table on the left side tend to hold their electrons in more closely, making the atoms smaller. Things over here on the right side tend to hold them more loosely, making the atoms bigger. So again, if you're comparing two things in the same row, let's say you're comparing tin versus, let's say, tellurium right here. The one that's bigger is going to be further to the left because that tin has fewer protons, so it's going to hold its valence electrons less tightly, making that atomic radius bigger. So tin would be the bigger of those two options. All right, this is something that's going to set us up to understand two more important periodic table trends. The first trend, once I pull up my new periodic table, is called ionization energy. So let me type that with my text tool here, ionization energy. Ionization energy is the energy needed to take away a valence electron. Oh, doesn't want to let me type. Energy needed to remove a valence electron. So, having a high ionization energy means it's very difficult to remove a valence electron. I need to take the size down on this. It means it's very difficult to remove a valence electron. Having a low ionization energy means it's very easy. This basically just goes in the opposite direction of our trend for radius. So higher ionization energies are found towards the top of the table and the right. So it increases from left to right and from bottom to top. Fluorine has a very high ionization energy, while francium has a very low ionization energy. The reason behind this is the same stuff causing that trend with atomic radius. If you have valence electrons very far away from the nucleus of the atom due to all these energy levels, it is very easy to take electrons away. So that ionization energy is low. If you have the electrons very close to the center of the atom because it has a very few energy levels, the ionization energy winds up being higher. We have to put in more energy to remove that electron from the atom because we have to fight the attraction between the nucleus and the electron. From left to right, again, if we have less positive charge in the nucleus, then we're not holding those valence electrons very tightly, so it's easier to pop a valence electron off. So our left side has pretty low ionization energy compared to our right side, which has pretty high ionization energy. If you've got more protons in the nucleus, that means that they're going to hold very tightly onto the valence electrons, meaning you have to put in more effort, more energy to take those valence electrons away. The last trend actually follows the exact same pattern as ionization energy, increasing from left to right and from bottom to top. And it is called electronegativity. So let me erase our ionization energy for a moment. It's called electronegativity. And it basically is the opposite in definition of ionization energy. Electronegativity is basically a measure of how attractive is an atom to an electron. So how easy would it be to gain a new valence electron? How likely would an atom be to steal an electron from another atom or to hold electrons very tightly in a bond? So how attractive is it? Having a high electronegativity means it's very attractive. Having a low electronegativity means it's not very attractive. So again, things in this bottom corner here have a whole bunch of distance between the center of the atom, the nucleus, and the valence electrons. That means that attraction is going to be low. It's not going to be very easy for that atom to gain an extra electron or to attract a new electron because there's so much space between the nucleus and the outer electrons. It's kind of like when you play with magnets. If you spread two magnets further and further out, the attraction between them diminishes. It gets less the more space you put between those two magnets. The closer you bring them together, the more attraction they experience. And again, from left to right, so from column 1 over to column 8, right, it increases because we're putting more and more protons in the nucleus. We're increasing the charge of that nucleus, making it more positive, which is going to hold onto electrons more tightly and be more attractive to new electrons. There is one important thing that needs to be said when it comes to electronegativity and that left to right trend. And again, I'm just going to open up a brand new, fresh periodic table real quick. So, only other thing to know about electronegativity, when it comes to our noble gases, we actually assign them an electronegativity of 0. They are not electronegative at all. Because they're so stable and they have a full octet, a full set of 8 valence electrons, or in helium's case, a full set of 2, they really don't want any extra electrons, so they're super not electronegative. They don't want any extra electrons. So if you are ever asked to rank things in order of electronegativity, and you have a noble gas, that noble gas will always be the lowest value on that list. And so with that, we have learned all 3 periodic table trends that we will be focusing on. Atomic radius, which again, we have bigger atoms at the bottom, larger atoms to the left. Ionization energy, exact opposite. And electronegativity, same direction, except that our last column, noble gases, have electronegativities of 0.